for today. This is just for bonus point. It's not required. And let's see. So last time I just briefly mentioned something about the Gaussian animation. No, I know where's the Gaussian animation part. It's on the laptop here. It's on the this part. No, it's on this part. It's in the computer here. So from the last time, yes, that's the one we have from the last time. We have talked about the Gaussian animations algorithm, and this is the general situation. We do it, and then this is a general matrix, and then we put the left-hand side coefficients here, and then the right-hand side coefficients here, and then we are doing the Gaussian animations in this way. And we have, let's see, we have several things here. The step one, and then for this one, we would do n-1 iteration to get the things below the diagonals to 0. And then for each step, we would use the step 2, step 3. For each iteration, we are doing the step 2, step 3, step 4. And then for the step 2 and step 3, we are preparing for the row elimination here. And so we need to ensure that the things we use here, that is the diagonal elements we are going to use in the row elimination, is not 0. Otherwise, the ratio here is not well defined. And also, when you find out that there's a non-zero elements, the first non-zero element is in this column, and then we are going to switch 2 rows and then to prepare for the step 4 row elimination. And that's all the things. And will I give you one example, one concrete examples? I believe I have already given you one concrete example here. And then that's the examples 1, 1, 1, 2, and 1, 3 here. And let's see. So this examples at the end of the day, what you need to do is to use the backward substitution. Once you get to this part, and then you are going to use the backward substitution to solve this equation. So here is another part up to the Gaussian elimination. You need to solve this linear systematic equation. And at the end of the day, you need to use the backward substitution to solve the for the substitution process to solve for the x1, x2, x3. So from the bottom to the top, and then we got x3 equals to 2, and then x2 equals to 1, and x1 equals to 0. And this is how we solve the equation. But this is by using the apply the backward substitution process to the result matrix we get from the Gaussian animation. So now, this is all the whole procedures with the Gaussian animation. And now I'm going to count something. Let me see. So I'm going to count something here. Let me see. I'm going to come on here first, and then before I change to the iPad to present something. And this is the Gaussian animations things. Let me see. And I am going to count something here. Okay, thank you. Turn left, to the left. Okay, I'm going to draw this part too. It's not letting me to do the circle things. Let me see. Okay, never mind. So what I'm going to do is to give me some space, please. Okay. I just need the Gaussian eliminations part, and then I'm going to count how many operations do we need here. So let's see. So here for the step 5, step 6, and then that is the actual operation here, right? And then for the step 5, we did one. Let me see. We did one division here. And then this one is just one division, right? One division. And then for the step 6, how many multiplication do we need here? So we are multiplying the Rij to the Ei, and the Ei it should be already diagonals. So it should be already 0 here and then number here, right? So how many elements do we have here? It's m minus 2 and then plus 1, right? So if this is the J row, and then we have so for example, if this is the index for I iteration, and then how many multiplications should we do here? We should do multiplications for, so for that, this is step 5, and then for the step 6, and then how many iterations, multiplications do we need here? The multiplications we need here, we need C n minus I plus 1. Does that make sense? Because here, so for example, this is for the iterations I, and then we need to do, this is the iterations I, and then we have A11, A12, and then A1n, and then to the AII, and then to the AIN. And then we are going to multiply the Rij with this row, with the whole row here, all the elements here. So how many elements do we have here? That is m minus I plus 1. So we need to multiply this number to this element, to multiply this number to this element. So we have such many multiplication for the step 6. And for the step 6, we also have up to the multiplication, and then we need to do the subtractions, right? And then so for the subtractions, we are doing the same number of the subtractions. Actually, we have m minus I plus 1, and then subtractions. Just for one step 5 and step 6. But how many steps do we need here? We need n minus I plus 1, right? For this big step 4. So, and the step 4, and then we have m minus I iteration here, operations. So this means that we need, so for one step 4, and then how many, for just one step 4, and then how many operations do we need? We need, so for the division, we need n minus I. That is n minus I times 1. And then how many multiplications do we need? That is n minus I. And then n minus I plus 1. And how many subtractions do we need? We need n minus I, because we did n minus I iterations in this step 4, and then n minus I plus 1. This is for the division. And this is for the multiplication. This is for the subtractions. And now let's go to take a look at the back loop. So this is the loop, and then step 4, step 5, step 6, and then I just ignore the row exchange here. Let's skip how many row exchange do we need here. Then let's assume that we can do the Gaussian elimination without any row exchange. And so for the step 1, this is the bigger iteration here, right? The biggest iteration. And how many iterations do we need? We have we need the I goes through 1 to the n minus 1. So this means that, so if we want to finish all the Gaussian eliminations calculation here, and then we need, how many divisions we need to do the sigma sums from I equals to 1 to the n minus 1. And then also for the multiplications, we are doing these things, n minus 1. Sigma sum I equals 1 and then n minus 1. And if you keep doing the summation here, you will find out that this operation here is approximately, if you count this number of operations, we need to finish 1 Gaussian elimination, and then you will find this is the big O, and then which means that we have this magnitude of the operation here, and it's approximately 1/3 and the n cubic. And then the n is the dimension of your matrix, the dimension of your problem. You have n unknown variable here, and then your matrix A is n by n matrix. Does it make sense? So how many operations do we need here? And then it depends on the size of your problem, and this n is the number of operations you need is the big O 1/3 and the n cubic. Does it make sense? So if you compare to the what we have previously, we just use the another methods. Do I count here? So I think I didn't. Okay, I haven't include here, but that is the forward and backward procedure, and then but at the end you need to use the backward procedure to do the problem, right? And then to solve for the solution, and then for that part you have ON squared. That is for the backward and forward procedure. If you go back to check the numbers I gave you last time, and then this is for the forward and backward procedure. Forward and backward procedure here. And but this part is for the Gaussian elimination. This one is the Gaussian elimination procedures. They're the computational cost. You need 1/3 n cubic operations here. Sorry, I cannot move this table. This is the ON square. But now what I'm going to tell you, so is something's new, is if you have such an n by n system, and but now let's consider if you have an n by n system, but this n by n is veritable, maybe 1,000 by 1,000, maybe 100 by 100, 3,000 by 3,000. It's a very large matrix. Then this would become, if you use the Gaussian elimination to solve it each time, and then the number of the operations would become very terrible. And most of the time, if you take a look at what we have from the physics, from the engineering problem, a lot of time you have a matrix, and then AX equals to B, and then you want to solve this, right? And a lot of time from the engineering problem, the physics one, and then physics and some engineering things. And a lot of time, the problems coming from the applications, the linear system or the equation, this part mostly the A matrix is unchanged. And then the things is changing is the right-hand side. A lot of time, the right-hand side is changing, and then you need to solve for a new solution X. So which means that a lot of time you get the B1 and then B2 and then different vectors on the right-hand side, and then you need to, this is the input, and you need to solve for the new solution that is X1, X2, and X3. And so now the question is that if you want to use the Gaussian elimination to solve this each time, and then let's say this is this is such a big system. This is the let's say this is n as n by n is 1,000 to 1,000. And now the questions becomes that if you use the Gaussian eliminations to solve this one, and then maybe you have B100's input, and then you want to solve for X100 and then X1 to X100, and how many operations do you need here? The operations you need here is, so for example, one Gaussian elimination is 1/3 n cubic, right? And then it's approximately equals to O and then O 1/3, and then this is 1,000 and then cubic. And but here we have 100 input here, and then we have, which means that we have 100 and then times this big O operation here. At the end, how many operations do we need? Approximately, we have big O and then 10. Ooh, the number is super big. 3, 3, and then 9, 9, 9, 2 is the 9, 2 is the 11, 1/3. It's still big. But now I'm going to give you one method, just reduce the computation cost a little bit, and then so now I'm going to give you one thing. It's called LU factorization, and it's based on the this one is based on the Gaussian elimination, and the benefit of this Gaussian LU factorizations is, so I will tell you this computational cost of the LU factorizations here is just around the 1/3 n cubic, and then you don't need to do it 100 times. So at the end of the day, this one is better, but it's not super better. It's just like 10 to the 9, but you just reduce it to reduce the you don't need to do the Gaussian eliminations procedures every time, so we reduce it to the 10 to the 11 to the 10 to the 9. And this is the LU factorizations we are going to talk about here. And it's saying that we are going to get this LU factorizations based on the Gaussian elimination. And the benefit of this LU factorization is that you have the same A matrix, but you have the different right-hand sides. And you just need to do the Gaussian elimination once and then record the information, some essential information from the Gaussian elimination, and then you can keep doing the backward, forward substitutions for the same the recording message, and then which means that at the end of the day, you just need to do the Gaussian elimination once, and then you can use those information to solve the system of equation for the different inputs here. And this is the saving here. So I will tell you this in details. So I'm giving you one example how to record the message informations to the one matrix here. So LU factorizations, if you take a look at the name, and then L represents, so LU factorizations, which means that we are going to decompose the A matrix into two parts. and then that is the L matrix, and then U matrix. L, it means lower left triangular matrix, and then the U is upper right triangular matrix. And I'm going to draw the pictures in case you don't know the lower left, it means we have some non-zero here, and then 0 on the upper right. And then for the upper right triangular, which means that we have the non-zero elements above the diagonal. And then this is the 0. And this is why we call it LU factorizations, which means that lower left right triangular and the upper right triangular matrix factorizations. And so now what I'm going to do is to get to the one example for you. I'm not going to talk about the derivation part again, because based on the feedback, no one is interested in that part. But actually, you should be curious on that part. The textbooks has included every aspect of the derivations, and the textbook I suggest you to use is the first one, not the second one. A student complained to me about the textbook is quite confusing. The second one is confusing. The first one is very easy to understand, so use this first one. And so now I'll just give you one example to see how to record the information in the in the Gaussian elimination. So let's see one example. So I'm going to let you see. So this one is the result. So this is the results matrix after the Gaussian elimination. And that is the upper right triangular. If you remember what we did in the Gaussian elimination, this is the desired matrix. We want the upper right triangular matrix. And what is the L? This is something we want to record the Gaussian eliminations procedures. Gaussian eliminations procedures. So now I'm going to give you one example how to decompose the A into L and U. So this is the example here. I get an A matrix, and then I have 1, 1, 0, 3 here, and then 2, and then 1, negative 1, 1, 3, negative 1, negative 1, 2, and negative 1, 2, 3, negative 1 here. And now I'm going to do the LU factorizations, but all the things is quite similar to the Gaussian elimination. And so what I'm going to do, I'm going to create the L first, and then the L looks like this. L is designed to record the information throughout the Gaussian elimination procedure. So I'm going to create the L matrix first, because this is a 4x4 matrix. I'm going to create, this is also a 4x4 matrix. On the diagonal, they are 1, 1, 1. And then I'm going to fill out the following things here. The things below the diagonal. This is a lower left triangular matrix, right? On the diagonal, they are 1s. And then below the diagonal, that is the information we are going to record from the Gaussian elimination matrix. And because this is a lower left matrix, and then above the diagonal, they are 0, 0 here, 0 here, 0 here, 0 here, 0 here. Does that make sense? So now I'm going to process the Gaussian elimination, and then you will see how I record the information here. And this is the matrix A. Once again, this is the matrix A.
1, 1, 0, 3, and then 2, 1, negative 1, 1, and then 3, negative 1, negative 1, 2, negative 1, 2, 3, negative 1. And then I'm going to do the round 1 operation, the row operation. And then my goal in the round 1 iteration is to get this one to 0, get this one to 0, get this one to 0. If you go back to take a look at the ratios we got from the for the Gaussian elimination, the Rij it equals to what? It is equals to a let me see, it should be the Rji. The Rji, this is the I column and then J row, and then it should equals to Aj and divided by Aii, okay? And now I'm going to give you one information here. So for the first round iteration, if I want to eliminate this part to be 0, and then what should I do? If I want to eliminate this part to 0, and then I need to have, I'm going to change the row 2 and then use the row 2, and this is row 2, and then subtract, and then subtract the ratio should be A and then 2, 1, and divided by A, 1, 1, right? And because the ratio definition here, and then minus the row 1, and then replace this one, use this result to replace the original row 2. Does that make sense? And we are going to do, we want to also eliminate this part to 0, and then what we did here is the row 3, and then subtract the A31 and the A11 and the row 2 here, row 1 here. Row 1, and then replace this with the row, replace the row 3. And then for the row 4, we want to eliminate this part to be 0. And then we have A41 divided by A11, and then times the row 1. And then replace the original row 4. And now, the important information here is just the ratio and ratio and ratio here. And I'm going to put the corresponding, you could see this part is corresponding to the ratio here. This part is corresponding to this ratio. And this part is going to corresponding to this ratio. So I'm going to put the ratios here, A21, A11, and then A31 divided by A11, and A41 divided by A11. And I'm going to calculate the ratio here. And these are the values, and equals to, that is just the 2 divided by 1, and it's just equals to 2. And this is equals to 3 divided by 1, and then it's just 3. This one is negative 1 divided by 1, and then that is just negative 1. Now I'm going to do the actual row exchange here for the round 1, the row operation, and then I got this. So from the round 1, I got the matrix 1, 1, 0, 3, and then 0, negative 1, negative 1, and then negative 5. Am I right? 0, negative 4, negative 1, negative 7, 0, 3, 3, 2. And I'm going to proceed to the second round row eliminations in the Gaussian eliminations. And then for the round 2, and the goal is to eliminate this part to be 0, and then also eliminate the part for this one, the 3 here to be 0. So for the orange part, and then we are going to use the, so we are going to change the row 3. So this is the row 3 place. Minus, and then we are going to use the second row to animate the third row. And so here we have the second row. And then what is the ratio? The ratio should be the A23 and then divided by the A22. So here we have A32. A32 divided by A22. A22. And I'm going to use this result to replace the original row 3. And this is how I did it for the -4 to eliminate the -4 value here. And next, I'm going to eliminate the 3 number here. And then I got row 4, and then subtract and then the row 2, and then with the ratios 4, 2, and then 8, 2, 2. And then replace this one, replace the original row 4. And this is the second round of the operation. And I'm going to use the L matrix to record the ratios information here. Does that make sense? So here, I'm going to record the ratio information, and then that is just the A32 divided by A22. A42 divided by A22. And the number should be, so if you take a look at the matrix, what we have here, the A32 here is just -4. And then this one is just the -1. So I'm going to have, but the A32 here is not the A32 in the original matrix. It's the newly updated matrix here, the element here, A32, and then divided by A32, and then this is A42 divided by A22 here. This one, the number here, I'm going to use is the A32, and then that is -4, and then divided by the -1, and this one should be the A42 is 3 divided by the -1. So I got 4 here, I got -3 here. And this is the L matrix, and I'm going to do the actual round 2 operation here, the row operation, and I get this one. The matrix looks like this. The matrix, I got 1. I got 1, 1, 1, 0, 3. This is after the operation, the row operation, the round 2 operation here. And then I got this matrix 0, -1, -1, -5, 0, 0, 3, 13, 0, 0, 0, -13. And obviously, we get to the design matrix because this is the diagonal. And then all the things below the diagonal are 0. So what should we do here for this part? We don't need to do anything. So what about this part? Look at brain. No, this is a matrix. So we are going to put 0 here. Because we don't need to do anything about the column 3. So it's actually equals to the ratio 0 here. And so I'm going to put the 0 here for this part. And this is my L matrix. So at the end of the day, what's your L matrix and then what's your U matrix? This is your U matrix. This is the U. And this is the L matrix. Is that easy? How to do the operation here? And so now I'm going to say, okay, this is my conclusion. A equals to L times U. And then what's my L? L is just the 1 0 0 0 and then 2 1 0 0 3 4 and then 1 0 -1 -3 0 1 here. And then my L matrix is the upper right triangular matrix I get from the Gaussian eliminations matrix eliminations procedure. And then that's the one I get. Zero, 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 -13. And this is what we have here. And at the end of the day, you need to solve for this equation. And what you need to do is to, the original problem is there's just a matrix, right? If you have a B vector here, for example, you have a B vector, B equals to 1, 1, 1, 1, 1. And then what you should do is to solve these equations in this way. So now you have A equals to LU factorization, right? And then you want to solve this equation, AX equals to B. And then what should we do? It is equivalent to solve the equation LU, and then I just replace the X with LU, and then times the X, and then equals to B. And now I'm going to change this linear system of equations into two parts. And then the first part is I will let the UX equals to Y. And then I have L times Y equals to B. Does make sense? Because this is the matrix and vectors multiplication. And then I can do this multiplication first. U times X first. So I will give a new variable here. UX equals to Y. And then L times Y equals to B. And what's this system? This is the lower left. I'd like to remind you of this. This is the lower left equation, lower left. And then, which means that we can solve this one with the forward procedure. And then, so first we solve the Y, we solve the Y for the, with the, so step 1, and then so for the Y with the forward procedure. And I'm going to skip the concrete details calculations here, but you need to show your answers in details in your homework. And then once you get the Y, and then we can solve for, so this, so Ly equals to B, and then for the Y with the forward procedure, and then once you get the Y value, and then we will solve the UX equals to Y for the X, and then with the backward procedure, because we get a upper right triangular there. So because this one is upper right triangular, and then which means that we have such a shape for the linear system here. And then we are going to solve backward for this part. So forward for this part. Does it make sense? So the LU factorizations, you will see there are two parts. And then the first part is just the Gaussian elimination. So we just need this part of the operation here for the LU factorizations. And then once you get to the LU factorization, and then you need to solve the system with the backward procedure and forward procedure. And then that is why we have this many of the operations here. Does it make sense? So there are two parts here, but the benefit is that, so after the Gaussian elimination, you get the factorization, and then if the B, you have different B, and then you just need to solve this system, so for the X with the forward procedure and the backward procedure, and then just utilize the LU factorizations here. And this is the examples we mentioned today. And then next time, so if you take a look at what we have here for this example, you will find out that we can proceed the Gaussian elimination smoothly
which means that we don't need to do the step 2, step 3 in the Gaussian eliminations procedure, which means that we don't need the row exchange here. This is the LU factorizations. This is one requirement here. So this is the general criterion here, but later on, I will tell you how to determine whether this matrix need a row exchange or not. So for the LU factorizations, we need a matrix. This is the basic version. Of course, you have some advanced mode versions for the LU factorization, but here, for this basic factorizations, A equals to L times U, and then we need a matrix that can be, we need a matrix that we can perform the Gaussian elimination without row exchange. And this is one requirement for the matrix A here, without row exchange. But now the question is that without telling you, without going through all this Gaussian elimination here, you don't know if you need a Gaussian, you need a row exchange, right? So there's some mathematics ways to determine whether we need the row exchange here. So next time I'm going to tell you the definitions, but here this is the theorems about the LU factorization and the theorems, and then this is the theorem 9.1 on the first textbook, and this is about the LU factorization, and then it tells you when the matrix can have LU factorizations, which is equivalent to this statement here. We can perform the Gaussian eliminations without row exchange, but without doing the concrete details calculation, you cannot know it beforehand. So now I'm telling you one criterion to determine how we know it beforehand, that we can perform the Gaussian eliminations without row exchange. So here we need the A matrix to be an M by M matrix. And then also, I will tell you later on the definition of this second criterion next time, but it's saying that it's needing principles some matrix A1 and then to the AN are all non-singular. And then we have the conclusion that A has LU factorizations and their factorizations are unique. Stations are unique. It's unique. And this is the conclusions. This is the theorem about the LU factorizations. And then next time, I'm going to tell you the definition of the leading principal submatrix. And any question about the non-singular part? How to decide whether the matrix is non-singular? If you have questions, then I will also tell you the definition of non-singular next time. No questions. So next time I will give you the definition of leading principal submatrix, and then you will see how would we determine whether we can perform the LU factorization to a matrix. And that's all the things we want to talk about today. And if you have any questions, you can come over here, and we will have a nice weekend and homework. Goodbye.